continue this odyssey through liquid crystal science. So far, we talked about the Dometic and Dometic A, layer phases of the molecules standing up, and the Dometic C, layer phases of molecules tilting over. Now, just in this sort of scenario of rod-shaped molecules and layers, then this just sort of shows that there are a bunch of other phases. So part of today is going to be a sort of a survey of what the possibilities are in terms of molecular architecture and liquid crystal ordering.
Is there a simple way to see if you look at a molecule whether it's going to form in Dometic or Dometic A?
Well, I'm going to get to, just this next thing will sort of deal with that. So the Dometic A and C phases are phases of layers where each layer is a two-dimensional liquid. And these other phases have more order in the plane. The hexatic phase has orientational order, but the thermal population of edge dislocations in this in-plane lattice that reduce or eliminate the translational, in-plane translational order. And then there are phases that have crystalline in-plane translational order that become sort of indistinguishable from crystals. Okay, so what are the, say, for the Dometic and these kinds of phases, what are the minimal sort of elements of molecular structure? So you can explore that just starting out with just hard rods. So this is a phase diagram for a suspension or a system of rod-shaped, hard rod-shaped particles. Simulation was done by Dan Frankel's group. So this system has isotropic and Dometic and a Dometic A phase, and then higher densities. This is density going up here, and this is ratio of length to diameter. So that, this is the complete sort of scenario for this system of hard particles. This is an entropic. Everything here is entropic. So you have a Dometic phase, and then a Dometic A phase, where these things, again, get into layers. Now, the isotropic Dometic phase boundary, you see the simulation points here, then this red line is the line calculated by Onsager.
Can you explain the axis a little bit more?
Sorry, this is density, number density going up. So as we go from, at low density and sort of, more, less rod-shaped particles, we're down in the isotropic phase. You increase the density, and then, you get ordered phases. If if they're not anisotropic enough, then it just goes from isotropic to crystal phases. And if they're anisotropic, then you get isotropic, Dometic, Dometic, and crystal. Okay?
Rho star is volume fraction. If it's dimensionless density, how you define it?
It's
So it's a volume fraction.
basically the volume fraction, right? And L over D is the ratio of length and diameter. Okay, so Onsager was actually trying to understand the observation of Dometic phases in solutions of tobacco mosaic virus, which is a rod-shaped virus, experiments that were done by Burnell. So let me just sort of sketch Onsager's argument. He calculated this phase diagram using basically comparing the sort of interplay of orientational entropy and translational entropy. So if you have these rods in the isotropic phase, then they tend to encounter one another. If they line up, then there's more sort of freedom for their centers of mass to move around. So the centers of mass depend on an excluded volume, and the excluded volume turns out to be for each particle, turns out to be the volume that you would get by sweeping, by rotating it about one of its short axes. So you get this sort of disc-shaped volume. So that's in the isotropic phase, that's the effect of excluded volume of each rod. And as you increase the concentration, when these volumes overlap, then you get a transition to the pneumatic phase. And if you work out the geometry, then this is the red line here. The volume fraction is just the ratio, this critical volume fraction is the ratio of diameter to length in this model.
But what,
Pardon me?
Sorry.
what specifically is shown by the red line? There are two lines of coexistence in the...
Well, there's, in the actual simulation, you have
in
you have
simulation I see
coexistence.
two, but
The red line is where the transition is. The Onsarger model also has phase coexistence, which
that's right, yeah,
yeah.
so there should be two lines.
Yeah, there should be two lines, but they're generally in where the red line is.
Two borders of this red line with that.
Right. Well, it's wider than that, actually.
And it's,
On the left-hand side, your V, it's V rods over V. That V is an excluded volume from the one underneath it.
V rods is the volume of the this is the volume fraction. So this is the
Yeah.
volume occupied by particles divided by the total volume.
Then why is it NL squared over, or NL squared D on the next line?
So the total volume LD squared, that's the volume of a rod,
Yeah,
times the number of rods,
yeah,
divided by this is divided by the excluded volume. The excluded volume is L squared D. The occupied volume is L D squared, the excluded volume is L squared D.
right, okay. So
That ratio-
on the left-hand side, V is excluded volume, and on the right-hand side, there, you change notations?
No, because it's rho C, so it's volume which corresponds to critical condition.
This is a
Yes.
this is a critical volume.
Thank you.
Okay, so this just shows a symmetric A phase. So how do you get, let's say, tilted phase? So here we take this spherocylinder and then just add flexible tails. Again, it's a hard molecule with this sort of flexible spherocylinder tails where we can adjust the flexibility of the tails. So there's an energy cost of entropy gain and energy cost of disordering the tails. So this is a computer simulation, and this model shows much broader polymorphism, shows all the main phases that or many of these phases in that previous summary, pneumatic, smectic A, smectic C, and then these phases within plane exadic order, one where the molecules are tilted toward their nearest neighbors in plane, and one where they're tilted toward their next nearest neighbors. That's smectic F, that's smectic I. So
it's actually,
sorry?
there it's actually C2 symmetry, no one tails, right? It's actually not hexatic anymore. You're tilting along one of the left vectors, one of the six left.
Well, it's hexatic, but with this broken, there's a
Right.
broken symmetry.
So it's actually
Because
the end
of
of
the
C2, right?
Yeah. Okay, so this is the phase diagram you get in this. with this model. So here, the vertical axis is pressure, going from low pressure to high pressure, and the horizontal axis is temperature. So this is high temperature going to low temperature. So you see that the elements of the molecular architecture that you want to get this tilted phase diagram is a rigid core with flexible tails. Okay, so the tails tend to want to increase the area per molecule, and one way the molecule, because of entropy, and one way that can happen is that you have the molecules tilt over. Molecules tilt, and their aerial projection in the layer increases. So the tails push the molecules apart. That's how you get these tilted phases. So generally this tells you what architecture you want, but it doesn't tell you what molecule to make.
How does the length of tail enter in this?
You tend to, I think.
Is there a combination of parameters that you would choose? Is it bending and length together? Or?
Yeah, no, I mean, as you increase the length of the tail, the tendency for layering gets stronger.
Is there a theory that describes it? Or?
There's a very early description of that by Bill McMillan in the 1970s. He showed that, I mean, generically, if you have phase diagram, you have the length of the tails, you end up with a phase diagram that goes something like this: I, N, and symmetric A. In systems with a symmetric A phase. So symmetric layer ordering is sort of enhanced by making the cores, which are sort of attractive, a smaller fraction of the total layer.
But the bending should also enter there, the bending stiffness.
It's hard to vary it on molecular. Well, it would enter, I think.
Because here you're bending it.
Well, this flexibility, this is a combination of temperature and energy.
Maybe there's some effect to that.
Yeah.
Right. That's pretty much.
So, this shows that, we have, you can sort of get a grip on what the, what the basic elements are of getting a certain liquid crystal phase. But again, this doesn't tell you exactly what molecules are. It says you want molecules with hard cores and flexible tails, but that still leaves you with a large, a large range of possibilities. I put these two slides in this morning, they're not in your notes. So this is just to show that we've been talking about these tilted symmetric phases where you have a uniform, the tilt and alternate layer directions is the same. There are also phases where you have that are anticlinic, so you have opposite tilts and opposite layers. And this comes about in this case because in this molecule you have a tail which tends not to not to be straight. When it sort of at this bond with the core, it sort of bends to be parallel to the layers. So this tail suppresses out of layer fluctuations, so it keeps the molecules in the layers. So if you have fluctuations in the tilted phase, if you have fluctuations in the molecules out of the layers, that tends to promote the same sign of same direction of tilt in adjacent layers. Once you suppress this tendency for out of layer fluctuations, then there's an inherent tendency for the tilt to become anticlinic, which I would say is still not really understood on a molecular scale. but there are these antiferroelectric or anticlinic phases, and then variations of that where you have phases where all the alternate layers are tilted in opposite directions. This is looking down. And then a phase with a 3-layer periodicity, so tilted, this is the first layer, the second layer, the third layer, in a 3-layer repeat. So you have phases that go up to 4 or 5 layer periodicities. Okay, so then earlier I mentioned the making nematic phases with disc-shaped molecules, but this sort of same, okay, so now I should say, not to say one thing here, and that is that the tendency to get symmetric polymorphism in these structures that have rigid core, these flexible tails, is a form of nanophase segregation of rigid entities and flexible entities. So rigid and flexible do not like to mix. And this is kind of the shortest length scale manifestation of that in soft materials. And you see it quite clearly that in the in these tail regions, these the sort of flexible entities can accommodate each other and maintain their entropy. But as soon as they try to get in between these straight rods, then they get straightened out. That costs entropy. Flexible and rigid don't mix, or don't like to mix. All right, so then the same thing works for disks. You put long tails on the disks, and then you get nanophase segregation in the disk phases into these columnar phases. So these are the disk analogs of smectics. These can have various kinds of in the columns. You can have very well ordered columns. You get columns with sort of helical precession of the orientation of these molecules, or you can have columns that are disordered. All right, so these smectics are sort of indicative of this second pathway to making liquid crystals, and that's the introduction of interfaces, making soft interfaces. So this is a major sort of theme in liquid crystals. This shows a couple of examples of, so here's copolymers of hydrophobic and hydrophilic molecules. This is a simulation of, and here we have water. Oh, sorry. This is a bilayer film in water with the hydrophobic parts exposed to the water. So this shows individual molecules. So if you create interfaces then orient molecules, so you get anisotropy, orientational anisotropy, as well as positional ordering in systems where you build interfaces. So major ways of doing this are block copolymers and amphiphilics. So molecules with strongly different sort of chemical attributes. In this case, we have a fluorinated hydrocarbon with an ionic end forming in water. This is a monolayer. So this is a single monolayer, but in a bulk phase, this, for example, could be a section of a layer in a layered liquid crystal. Okay. So the interfaces drive liquid crystal formation. Okay, so general example of this are block copolymers, where you have this sort of grafted molecule with in this case polystyrene. So you have a linear molecule, half or part of which is polystyrene. Then there's a bond to this case polystyrene, polymethyl methacrylate. Okay, so this shows the sort of sequence of phases you get as you vary the relative volume of PMMA and polystyrene, which you control by how long you make the chains. You just sort of build that into the molecules. In this case, with polystyrene is the sort of the minority phase. You end up with sort of little polystyrene balls in a matrix of PMMA. Then cylinders, sort of equimolar volumes, create a lamellar phase. Again, this is flexible. This is more rigid. So if we were to take this molecule and cut it in half, then these two solutions in a melt would just face separate. So the molecular connection forces them to sort of make these nanoscale structures with characterized by this interface. Okay, now this is a theme which can be sort of worked in, in a huge range of ways. The thing in the middle is the phase diagram showing, in this case, temperature is going down on this plot, and relative volume of the two phases going from left to right. It's calculated using the mean field theory. You can make tri-block copolymers and get a range of more complex structures. But again, the principle is the same. You have three moieties which are to some extent immiscible. You can vary the relative volume of the three, and you have then two sets of interfaces which will, will organize in various ways. So these are all the crystal phases. Now, this sort of behavior was this interfacial driven with the crystal formation was really first observed in surfactants. So here, this is sodium lauryl sulfate, so a sulfonated ionic and aliphatic tail. So this shows the phase diagram as a function of concentration of this amphiphile and temperature on the vertical axis. This is a isotropic phase where you may have, this is micellar phase, so that's shown here. So micelles of the surfactant in water, but as you increase the concentration, then you get these bulk phases. Now, the basic, in this case, of course, the lyotropics, these kinds of phases include the lipids, right, which I haven't drawn here, but they have very similar, basic behavior. Controlling factor here is the interface curvature. So if you make an interface that tends to be flat, then you get lamellar phases. If it tends to be curved, away from the water surface, the water fraction, then you get, for example, these cylindrical or micellar phases. So you can control the interface curvature by the nature of this head group, by the length of the tails, the number of tails, and concentration. Well, ion concentration, for example, will control the relative repulsion of these ionic groups in this interface, and that manipulates the curvature. Okay, then, so these are the basic lyotropic phases that we saw for the polymers. Then there's a broad polymorphism within this theme of different kinds of phases. So the basic lamellar smectic A, but then phases which are lamellar, but where these layers are modulated. So, for example, if you can make you have a surfactant, for example, that tends, to have an interface that's curved away from the water layer. And here's a surfactant that has an interface that tends to be flat. Okay. So now, if you make a mixture of these two, then the surfactant that tends to be curved can phase separate and form these pores. The boundary of the pores is a curved interface. So the surfactants that tend to be curved will phase separate and form pores. So you get this kind of modulated phase. Okay, but fairly rich polymorphism.
I have a question. Just a basic question. What does lyotropic mean?
Lyotropic means that back here. So there are basic division you can make is thermotropic and lyotropic. Thermotropic, where you get various phases by changing the temperature. So here you're getting various phases by changing the concentration. In many of these soaps, room temperature is, say, here. So you can go along in concentration, get these various phases at room temperature just by changing the concentration.
You still seem to be temperature dependent, right? You can get,
Well, yeah. So it's
Just
a vague,
less so.
it's a vague, it's a vague distinction.
it's just more or less temperature sensitive. That's-
Yeah. Right. I mean, they're all temperature sensitive, dependent, but so another way of thinking about iotropics is you're making a mixture of a molecule which by itself may or may not have liquid crystal phases. You're making a mixture with water which is never going to have a liquid crystal phase. Okay, and then you get a liquid crystal. So that's another way of thinking about lyotropics. You wouldn't call block copolymer a lyotropic.
So at 100% this molecule don't form liquid crystal.
They may have a thermotropic, they may have thermotropic phases.
And the terminology is the other way around. If you have a thermotropic, if you add water, do you have go to different phases or typically not?
Yeah, I mean, there are thermotropics that have, like, groups that have hydrogen bond, for example, which you can swell with water.
You can change phases.
You can change phases by putting in water.
So the definitions are very,
Definitions are very,
Okay, but it's,
definitions are very, liquid crystals are very difficult.
but the ones in your, laptop displays, those are thermotropic.
These are thermotropics.
So they have no single component, it's just liquid crystal molecules, there's no water there.
Well, it's a mixture of liquid crystal molecules, but they're all these organic things
Right,
with,
there's
you know,
no
non-organic
non-liquid
and aromatic sort of groups.
On that.
All right, so lytropic liquid crystals have, very, some broad application. I mean, if you know, the liquid crystal display industry is now $100 billion a year business, at least. So you'd think, well, so if I looked into what in Web of Science, I just search under liquid crystal, what's the most cited liquid crystal papers? You think, well, it's probably displays, having to do with displays or something. That's been a giant activity. Turns out that that's not the case. So, so this is the number one cited liquid crystal paper. So it has 9,000 citations, and it's to making mesoporous silica using lytropic liquid crystal. Okay, so you start out with with one of these lytropic, one of these phases. So you have surfactant and water, and then you put TMOS, which is a submethylated silane, which is water soluble in the water. Then you change the pH, and silane polymerizes. So the water turns from water to silica. And then you just burn out the liquid crystal. Now you're left with silica with these, 20 nanometer pores and periodic array of 20 nanometer pores. Okay, so this is very interesting for refineries. So actually 10 of the top 20 papers in liquid crystals are on mesoporous silica. And if you search mesoporous silica, then the same papers are the top papers in mesoporous silica. So liquid crystals have sort of spun off this field of making mesoporous silica.
What are they used for?
You treat the inside of these pores to be catalytic. So then you make this, you make this stuff in a powder, and then it's used for catalysis of hydrocarbons. I don't know too much about that.
What scale do you make these? Like how long?
How long?
Yeah, like
Oh.
or do they? Is it all small order or is it?
Well, no, I mean, long is like microns, or, if you grind it up into a powder, it's probably a few microns. Okay, so let me just sort of finish this kind of sort of sweeping kind of overview stuff with a couple of other examples. So this is Virgil Perchek's work. So starting out with this theme of making molecular wedges with different sort of chemical functionality on the outside, and then in the middle, or at various places. So you create something like this. Okay, so then these things will self-associate in various ways. So you start with wedges, and then you can make these little cones or discs. Or if you make these things kind of fat enough, then they themselves look like cones. So then they self-assemble into these various structures, and then these various structures self-assemble into either columns or or spheres, and then the columns or spheres will organize into various lattices. So, so these are all columnar phases, columnar liquid crystal phases, and then you can get this, the double gyroid cubic phase, or a variety of, if they make spheres, then you can get packings in the spheres. I think he's even gotten quasi-crystal structures in these packings of the spheres. And he's developing functionality in these structures, so using these things to make arrays of making this internal sort of section electrically conductive, making arrays of nanowires and sort of analogous and doing various other things, but kind of an amazing array of structures. I mean, they've been identified, so maybe on each one of these structures there's been one experiment. On the Dometic phase, there have probably been, 100,000 experiments. So this, invites experimentation. Another interesting theme is by Carsten Chersky, and this is the Boulder amplifiers. So you have a rod like like a spinel-based core. So the blue balls here are hydroxyls. So this is basically the blue is an aqueous environment. And then the side chains are fluoridated. All right, so these molecules will chain up into rings, segregating this side group into columns. You get structures like this. So columnar phases.
So which way does the rod run, let's say, in that column?
Okay, so the rods are little black lines here. So the rods are making rings
Oh, I see.
connected by these balls. So let me show you the next slide, which kind of is an example of this. Okay, so here's a molecule. It's got this fluoridated tail, this methylsilane, this phenyl-based core, and then these hydroxyls. So I could cut this molecule into, the hydroxyl part, the fluoride part, the silane part, and this phenyl part. They all hate each other. They would all just separate into, you get 4, drops of these different things. Okay. This molecule is sort of pushing this notion of internal, sort of building in internal frustration by connecting things together in a molecule, to an extreme. But you end up with, in this case, columnar phases with structures like this. So in here, the rod connecting two vertices is this thing. The blue spots at the end are the hydroxyls. The silanes are the yellow, and the fluorines are the green. And that just comes out in columns.
Why are the two sensory groups are different? If they would have been the same,
Here and here. Well, if they were the same, then you would probably go back to. If they were the same, then they would probably come around on the same side of the molecule, and you would have something that looks like this. Then you get something that looks like, these kinds of structures. So anyway, in terms of sort of pushing the the boundaries of, you know, what kind of phases can you make, and, you know, sort of controlling and understanding this morphology or the structures that you get with internal frustration. This is kind of the state of the art, I would say.
What did you vary to get the different pictures?
Sorry?
What did you vary in order to get the different A, B,
Oh, what
C?
do you vary? Okay, I'm not sure. There's, this may be the length, you vary the length of the tails, for example, and the number of rings in this part, you know, and you can put more hydrogen bonding groups at the end, so, you know, in this paper, there are, there are homologous series with different lengths of these chains and, you know, variations in the form. Then you get different, you get variations on these phases. Again, once you learn how to make, once you may start making this, then you do all the simple variations to see what happens. Okay, so then this notion of block copolymers can be, or this frustration notion, again, this is another kind of extreme example of a core, of this polyphenylene kind of core with polyether tail on one end. This is a highly water-soluble tail, and then aliphatic tail on the other end. So you make a molecule that looks like this. Put this in water, and the aliphatic tails stick together. The polyether tails are water-soluble, so you get a structure like this. These things associate, they form a bilayer. Then the bilayer organizes in various ways. In this case, depending on the alkyl chain length, you can get spheres or rings or perforated sheets or bilayer spheres. Another example.
That's into this solution.
This is in water, yeah.
If you increase concentration, they will do something there.
Well, then you would get sort of, this is a variation on this. You increase concentration, then you get phases. Okay, so one of the really nice sort of marriages of ideas has been the marriage of liquid crystals and polymers. So both from a sort of an applications point of view and from a fundamental science point of view, it's been very, very rich. So you can make liquid crystal polymers, main chain polymers, so where you have mesogenic groups, the kinds that we've been talking about, hooked together in a linear chain, or you can put the mesogens on as pendants, as side groups on a chain. And with this connection and various connection can be in the middle or at the tail. And then you can cross-link these chains to form gels and elastomers. Now, applications-wise, the main material has been Kevlar, which is shown here, which is a polyamide with strong hydrogen bond between. This is a main chain polymer with strong hydrogen bonding between these chains. So this makes a very strong material with very high tensile strength. So on the bottom here, it shows some examples of the thermal behavior of a liquid crystal elastomer. So you start with the elastomer in the isotropic phase, and you can, for example, do this cross-linking with light, so you can photopolymerize, so you can, say, melt the liquid crystal, melt the elastomer. So these materials will exhibit isotropic pneumatic phase transition, so you can heat to the isotropic phase, photopolymerize, so you get an isotropic cross-link network, then cool into the pneumatic phase, and you get pneumatic order, and accompanying pneumatic order will be a change of shape of the polymer. So now we have pneumatic order embedded in a deformable solid material, and you know that actually produces mechanical work. So you have a piece of this polymer here stretched out. This is the other going the other way, so it starts pneumatic, and then you increase to the isotropic phase, and the shape changes from this to this. Now, the physics of this, the coupling of the polymer deformations to liquid crystal ordering has been is a very interesting area. So you can imagine starting in the isotropic phase, cooling into this pneumatic phase. So you get an object of this shape, but you could have gotten an object of this shape if the sort of pneumatic order had chosen to go in the other direction. And so, this kind of orientational degeneracy makes it possible to sort of mechanically go from this orientation to that orientation. And it costs very little strain to do that. So you have what's known as soft elasticity, which Leo can tell you all about if you're interested. So you can start with pneumatic liquid crystals. Another sort of theme, starting with pneumatic liquid crystals with polymers that are side chain polymers that are soluble in the pneumatic, but terminated by insoluble groups. So at high temperature, this is a liquid, but if you cool, then these terminal groups associate, and so then you end up with a pneumatic gel, which in which the polymer will disorder the pneumatic, so that makes it something that's optically scattering. But if you put an electric field on it, then it becomes clear. Okay, so another very cool application of liquid crystal polymers are systems where you can photoactuate by incorporating azo pores. Okay, so the azo molecule on appropriate illumination goes from a trans to a cis form. So the molecule goes from being basically straight to bent. And in a polymer network, that produces mechanical, outwardly mechanical responses. So this is work by Vic Broer. So you start out with a layer of this polymer, of the monomer, sorry. And so this is like a 50 micron thick film or something like that. Okay, so you treat the surfaces so that the pneumatic director is parallel to the top surface and normal to the bottom surface. So this is the pneumatic liquid. All right, so then you photopolymerize these acrylate groups. So there's terminal acrylates on these things. So then this mixture of these 5 molecules, that forms a pneumatic polymer network. So now it's a solid material with this pneumatic deformation built in. Okay, so now you shine light on it. So when you shine light on it, the azos go from being trans to cis. They're along the director. So the the material then, when the molecules bend, the material shrinks in the direction of the pneumatic director. So the top half of this 50 micron thick film shrinks. The bottom half, where the director is standing up, shrinks in the other direction, which means that in plane it expands. So you shine light on, the top half of this layer shrinks, the bottom half expands. So it bends. Shine light on it, so so he makes by nano or microfabrication these little fingers, and then you shine light on them, and the fingers bend up. So you can make arrays of fingers that are sort of turning light on and off, arrays of fingers that are.
What's the time scale for this?
Oh, it's really, they're very fast. I mean, you know, there are, you know, you can oscillate these things at like 100 hertz. The full sort of range at 100 hertz. It's really, I'm looking for a movie, but I couldn't find it. But they're very impressive. You see the moving here. So there's quite a lot of work on putting these photoactive molecules into liquid crystal polymers. But I think the sort of prefabrication of a particular director geometry is really the nice feature of this. Okay, so another class of liquid crystals are the chromatics. Okay, so this is another example of fairly aggressive frustration. So you have, in the case of the chromatics, the kind of the hydrogen atom of chromatics is sunset yellow, which maybe some of you had for breakfast this morning, because it's a food coloring. All right, so the characteristic feature of these molecules is that they're like polycyclic aromatic hydrocarbon sheets, which are patently not soluble in water. But then they have around the edges things like sulfates or carboxylates or hydroxyls that are water soluble. So you have this competition between this insoluble core and these soluble edges. So that leads to, in water, to the formation of stacks of these molecules. So the hydrocarbons can sort of remove themselves from the water and expose the charge groups. So the individual molecules form columns. The columns then can form pneumatics or columnar phases. Now, now you may recognize that this is the basic structure of DNA. So DNA is kind of a polymerized chromatic liquid crystal. And we'll talk more about that in the last lecture.
What's the definition of chromatic again?
Well, again, the definition is a little vague, but
Rule of thumb.
rule of thumb, you have something like these aromatic sheets, which are, many of these molecules are dyes. And, chromatic aggregation is encountered in the dye business very, extensively. So there are dyes, or things like dyes, where you solubilize them with strongly ionic groups.
How is it different from the squatic you showed earlier?
The viscodics we showed earlier are thermotropic, there's no water.
So it's lyotropic viscotic.
This is kind of a lyotropic viscodic, yeah. Again, you could probably get these, if you could get them without water. Well, a lot of these things are very hard to purify, but if you could get them without water, then they probably would have thermotropic phases also.
But in the definition, is it, what's important in the definition? Is it the shape, the
No, I think
line, or the chemistry?
well, the shape in the sense that, yeah, there are these flat aromatic sheets with these salt groups or polar groups on the edge. I mean, I think that's as close to, definition as you can come to.
So if it's not color sensitive, it's not a dye, it would still be called chromatic?
So they're called chromatic because of this molecule, which is disodium chromoglycate, which is a drug that was developed by a French doctor to treat asthma. And he called it chromalin. So this, sort of the commercial name of this stuff is chromalin. And so this, the field of chromatics, sort of, this is one of the early molecules, and so the chromatic name comes from this. But they have interesting color effects because they have their dyes, and the optical absorption dipoles are in the plane of the molecule, so they're highly dichroic. So you can make, if you, well, this is showing an aligned sample between cross polarizers, so they're birefringent. But if you just had a polarizer here, then so if you align the columns like this, when the molecules get to be parallel to the polarizer, this would be strongly colored. If you rotate it by 90 degrees without the analyzer, then it would be clear. So they're dichroic. This shows the isotropic pneumatic phase coexistence with this disodium chromoglycate, where you add a depletant, you put a depletant into the solution also, which is spermidine, and that generates very interesting growth sort of morphology in this columnar chromatic phase. Okay, so we'll talk more about DNA as a columnar lipocrystal tomorrow. Okay, so now I'm going to go back to some of the basic, back to the simple pneumatic. So, in your crystals, you spend, time studying the basic phases. You can get those materials in large quantity, highly purified. There's a lot of information on them. So, there's continuing sort of work on the basic things. While you look at these very exotic things that we just saw in the last few slides, which are very hard to get and maybe not very pure, and oftentimes not exactly what the people that made them think they are. All right, so back to the pneumatic. So in these textures, we saw these beautiful Schlieren patterns. One of the features here, so you have these smooth brushes terminating in points. And you can have either 2 brushes coming into a point, or you can have 4 brushes coming into a point. So the number of brushes in the structure sort of reveal the topology of the molecular orientation. These are 2-dimensional patterns in this case. The molecules are all parallel to the screen, but changing as a mutual orientation. So in this drawings, the solid lines are representing the director, that is the orientation of the molecules. So for example, if you have a defect like this, you'll have in cross-polarizer and analyzer, 4 dark brushes. So that's a 2-pi rotation of the orientation. That's, but in a pneumatic, because this director N is equivalent to minus N, so we can have a pi rotation, so we can start out here, N pointing to the left, and go around, here N points to the right, and then we can connect up these two halves, because N is equivalent to minus N. There's
So
no,
you're not drawing rods anymore, so maybe you're drawing lines.
well, the lines are, the rods are sort of parallel to the lines here.
In the first picture, if the rods are on the circle, what breaks the symmetry determines the direction of your cross?
The polarizer and analyzer orientation.
So if you turn it, it was the turn visible.
Yeah, if you turn polarizer and analyzer, then these dark, the dark brushes will rotate.
Okay.
If you have this thing and you turn the sample, then nothing happens. Okay, so both of these, this is a +1, because in this case, as I go around the defect, the director rotates in the same orientation. That's plus, and if you can have the situation where as I go clockwise around the defect, the director rotates in the opposite direction, so that is the -1, that looks like this.
I mean, maybe it's good to point out that it doesn't matter how the director is oriented. I mean, you can have also.
That's this one, yeah. So this is so topologically, this is equivalent to this. Just every place you rotate the director by 90 degrees. So this is a +1, where directors are sort of pointing. This is a hedgehog defect in 2 dimensions.
But -1 has actual direction of a cross and a fifth rule.
Right, so the -1, so the +1, if you're in cross-polarizer and analyzer and you rotate the sample, then nothing happens. The -1, if you rotate the sample clockwise, the brushes rotate counterclockwise.
So that's how you distinguish.
Yeah, so these, these patterns can be sort of mapped out from the, by, manipulating polarizer and analyzer, rotating sample.
How do you distinguish the 2 + 1?
Okay, so how would you distinguish this from this? So in your microscope, you'd have a picture like this. So then, so there's, you obviously see the birefringence, but in this picture, you can't tell, say, whether the director here is radial or it's tangential, okay? The pattern will look the same. So what you do is, you put into the microscope a plate that just adds birefringence uniformly. So, and if it adds birefringence with the same sign, let's say as this, then you'll see the birefringence increase in this brush and decrease. The total birefringence increases in this brush, decreases in that brush. So then you can distinguish, this orientation from that orientation.
Can you also decross the polarizers? Does that help?
That doesn't help.
Maybe can you point out which defects are which and connect on these?
Well, no, I don't know. I mean, the +1s are the ones with 4 brushes. So here, and here, and here. And then the 1/2s are, the ones with 2 brushes.
And why is the last one, after hedgehog stable, looks like some high energy?
Sorry, this thing?
Right.
This,
Why would the untwist and lower the stress?
there may be a boundary condition at the core here that, Well, let's see, all right, so, you know, you may have a situation where if you get close to the core, it wants to be radial, but that this thing is in some, you know, in some environment where, you know, it wants to be, you know, tangential to the outside, so then you would have this. Now, you can ask, well, what happens when I get to the middle here? Well, pneumatic order has to go away. So the defect cores are sort of little isotropic droplets, fundamentally. Okay, so now
And little, you know, on the scale of the molecules?
we scale of a few molecules, yeah, maybe 10 nanometers or something like that. I mean, it could be hundreds or, you know, could be hundreds of molecules, but a small scale. Okay, so now, so that was a 2D image looking through the microscope. Now with confocal, sort of the advanced microscopy techniques, we can sort of look in 3 dimensions, and pneumatic defects in 3D are very, it's a very rich and interesting aspect of the physics of pneumatics. So you can imagine taking a sphere, treating it so that the molecules are radial, putting it in an oriented pneumatic. So then, you know, the accommodation leaves you with a defect, either a point defect or this is like a +1 hedgehog defect in 3 dimensions, or a line defect where the cross-section of this line looks like this. It's a 1/2. So the line is this structure, and then sort of imagine just translated perpendicular to the screen. So that makes a line, and that's what this line is. And you can see, so these are computer simulations. These are optical microscopy. So you can see these lines in the microscope. So this shows what happens if you have a pair of these particles in a pneumatic, you quickly quench into the pneumatic phase, then it's filled with these defect lines, but then gradually they have extra energies. There's a line tension, so the lines tend to become shorter and straighten themselves out, and then annihilate, so you'll end up just with, you know, with sort of minimal defect. So this shows one of the configurations of this line if you have a pair of particles. And then you can build 3-dimensional crystals where basically the interactions between the spheres is accommodated by in this case you have these Saturn ring lines around each sphere. So you can build with optical tweezers these 3-dimensional crystals.
What's the range of that interaction if you have 2 spheres? How far away can they feel each other?
There's 1/r, it's like a 1/r squared force.
And how many spheres can one line catch? Because in your crystal, you need to, each sphere has to be connected to many neighbors.
And this is a 2-dimensional crystal. So so you're seeing all the connections here. You can make 3-dimensional crystals.
But in 2D, it's 6 neighbors, so one line can connect three neighbors.
Well, okay, so in this crystal, they've taken spheres that have Saturn ring defects, and they've assembled them, put them together. Now, you can make crystals where you have things like this happening, where the line is around one sphere and then sort of switches to a neighboring sphere. Okay, so then there's a kind of a wild, story of, all the possible ways you can have these disclination lines threading through a lattice of spheres. So that's actually, this is from the Ljubljana group.
But without it, you're saying this with certain ring defects, there is still enough attraction to form a crystal.
Yeah, right. Yeah, I mean, you know, once you have the ring, then this has zero net topological strength. I mean, this thing with a ring can exist in a uniform nematic.
And so when two spheres come together, they attract one.
But there's still an attraction. So these spheres will dipole chain, like the islands that I showed yesterday. The Saturn ring spheres tend to you know, the neighbor will come down, you know, and sort of sit where I have my laser pointer, sort of a little bit offset. So, you know, there's sort of a lateral attraction between these guys in this case. So this shows an example of this structure. So you have a microparticle with this point defect. Okay, then you have a gold nanoparticle with treated with an alkyl monolayer so that the director wants to be perpendicular to it. And so this micron, this is actually gold nanodisk, so the micron particle is trapped to the nanodisk at a defect. This shows three-dimensional image of the chiral. This is two glass plates with a cholesteric chiral nematic phase. So imaging the helix of the cholesteric, and you know, visualizing the defects that you have in this helical, you know, in the periodic structure of the cholesteric. So you know, you have various kinds of of defects that show up. All right, so continuing on the theme of sort of the basics of the nematic phase. So we have these molecules. Okay. And you can see the fluctuations. You can see in the video yesterday, you have fluctuations on sort of all of every, you know, on a wide variety of length scales down to the single molecules. But in order for this phase to exist, if you think of a single molecule, you know, it has to be orientationally constrained. Okay. And so it's in a well of some sort. Now, that well can't be infinite, right? I mean, there has to be, you know, if you think, okay, this is the nematic is going up and down. This is the worst case scenario where you got a molecule sort of perpendicular to the average orientation. That has some finite energy cost. Okay, so, but it has to be big enough sort of to keep the molecule oriented. Okay, so
You mean a well from the neighbors?
by the neighbors, right? I mean, the orientation is coming from the neighbors. All right, so there's a simple beam field model of this that has been, you know, very, very successful and sort of expanded and sort of extended in many ways. But I mean, this kind of characterizes the basic physics. So we have these orientation fluctuations in orientation of the molecule. So you can think of a distribution of orientations. Okay, and in a nematic, you can write this distribution as as an expansion in Legendre polynomials, okay? Where the coefficients of the Legendre polynomials are statistical averages over this, this distribution. Now, the first one of these that matters is n equal 1. That's P2 of cos theta. So that's this. This is P of 2 cos theta. So this is taken, this coefficient of the first term in this expansion is taken as the fundamental measure of the degree of orientational order. So in 3 dimensions, if you average cosine squared theta, just have a rod and then you average in all 3 dimensions, this averages to 1/3. So S is equal to 0 in the isotropic case. If they're perfectly ordered, then S is equal to 1. So going from perfect order to isotropic, S goes from 1 to 0. All right, so we have this distribution. Then we can calculate S by averaging over the distribution, as I just said. And to do that, I'm going to sort of posit a form for the distribution, just calculating it from a Boltzmann factor, where the molecule experiences a potential, a local energy, that's coming from its neighbors, okay? So that's the mean orientational field coming from the molecular environment. Okay. So we'll calculate this orientational order by averaging P2 of cos theta over this distribution. Okay, so then we need a form for this potential. Okay, so then we similarly, we have this potential V of theta. We're going to similarly expand this, actually. So there are going to be some coefficients. Then there's going to be this average, and there's going to be a piece of cos theta. Okay, so this is a sort of a posited form for this potential. So what it said, well, okay, so we can always expand V of theta in Legendre polynomials. What this assumption says is that in this expansion, the lowest term, the n equal 1 term, this coefficient has 2 parts. It has a constant, and then it has this average of P2 cos theta. So it has the order parameter in. So this says that the more ordered the molecules are, the stronger this potential is. Okay, in sort of the simplest way possible. Okay, so this is the potential, and so that goes into here. Okay, so then S, you have to imagine taking this and putting it up here. So then we have an equation. Z is the partition function. This is just the normalization. So we have an equation that says S is a function of S, which you can solve for S. Okay. So the left side, if I plot the left side as a function of S, it's a line. If I plot the right side of the equation, it's sort of a line that has positive curvature and then negative curvature. Okay, so from that, you can solve that equation, basically a self-consistency condition, and you can calculate S, and when you do that, you get something that looks like this. So this is order parameter as a function of temperature. And So this is the pneumatic phase, and then there's a first order phase transition at this point to the isotropic phase, which is S equal to 0. So it predicts a first order transition with an order parameter S that's about 0.4 at the transition, and it jumps to 0.4 at the transition and then goes up as the temperature is lowered. Now, this average of P2 of cos theta is important because all of the tensor properties, like the dielectric tensor that we talked about, they depend on P2. So the birefringence is proportional to P2. So you can measure the relative values of the order parameter just by measuring birefringence as a function of temperature.
How good is this model?
Right?
How good of job is this doing?
It's good. I mean, you know, the data would start off like this and maybe at lower temperature deviate. I mean, if you took 100 pneumatics and plotted delta n, you'd get a sort of a band of data. So there's some variation, but qualitatively it works really well.
But the fact that, for example, the first order transition is
Yeah, it's the first, well, yeah, right. All right, so the next element of basic pneumatic physics is the elasticity. So as I mentioned, you look at these textures, you see that the pneumatic wants to be smooth. So it has some kind of elasticity. And so to sort of build a theory of that, what you do is say that, okay, so deformations correspond to spatial variation in the orientation of n. And so if there aren't any, then the derivatives of n will be 0. So we'll say that's the ground state. And then we'll sort of develop a field theory for spatial variations in the orientation of n. Where n, the magnitude of n is equal to 1. Okay? So the length of n doesn't change. All that changes is the orientation. All right, so imagine that, we're standing, we're in a pneumatic and the director is vertical. Okay, so then we're going to move around, and n is going to change orientation. So what are the possibilities? All right, so n is like this. So I'm going to move forward and backward. So then n can change when I move forward and backward. It can change in the direction that I'm moving, or perpendicular to the direction that I'm moving. Those are the only possibilities. If it changes in the direction that I'm moving, it's going like this. That's splay. Okay, that's this. If it's moving in perpendicular to the direction that I'm moving, it's going like this. That's twist. Okay, that's this. The other possibility is that n will change orientation if I move along the director. Okay, so then the only possibilities there are that, n changes goes like this, or like that. Both of those cases are bend. So splay, twist, bend. Mathematically, those show up as splay is div n, twist is n dot curl n, bend is n cross curl n. All right, so we can do a simple problem, the simplest problem. So we have a cell where at the bottom the director is, the surfaces are rubbed, so the director is north and south, and then on the top the director is east and west. And so what happens in between? Okay, so we'll say Z to be vertical here, along, from one side to the other, and theta is the angle of the azimuthal angle of orientation. Everything is in the plane parallel to the surface. So we have d theta dz. In this case, the only term that will will be non-zero, will be this one, the twist term. And it'll just be d theta dz. So this n dot curl n will be d theta dz. So the energy will be this, 1/2 k d theta dz squared. Okay, from this I can get I can do a variation and get an Euler-Lagrange equation, which just says that d second theta dz squared is equal to 0. Then this gives me a linear variation of theta from top to bottom.
For your last slide, I'm not sure I understood the curve. Is the curve the frontier between isotropic and nematic, or is it S in function of the temperature?
No, this is S as a function of temperature.
Then what happens at higher temperature than?
Well,
Dometic?
yeah, actually, when you look at the energy, you see that you have this curve only up to this point, and then beyond this point, the other solution, which is S equals 0,
I see.
is, you know, is,
This is an equation just for S, but you should also look at the
you have to,
relative minimus of the energy and compare that.
okay. So you get you get a linear variation of theta. So it's like stretching a spring. You know, every coil in the spring expands by the same amount.
So pi over alpha is like pi over 2 over L or something.
Right, yeah. Pi over 2L, right? Okay, let me just skip that slide. Well, so now we'll go on to a sort of a slightly, well, a lot more sophisticated and kind of relevant calculation. So this is the Friedrichs transition. So we start out with a cell that has homeotropic perpendicular boundary conditions on both surfaces, pneumatic standing up. Okay, then I'm going to apply a magnetic field with a positive diamagnetic anisotropy, which means that the molecules want to be parallel to the field. Okay, so they're going to tilt over in the middle of the cell first and get parallel to the field. So this is the Friedrichs transition. Now, you could also do this with an electric field with the situation where, well, in this case, if the dielectric anisotropy is positive, the electric field will just sort of stabilize this orientation. But if it's negative, then again, the molecules will want to tilt over. This geometry, you know, commercially right now is worth like $20 billion a year. This is exactly how the vertical aligned liquid crystal TVs work. You have this initial alignment, you put on a field, and the molecules tilt over. Okay, so we'll go through this, you know, this liquid crystal statics problem. And, you know, you can think of it as a magnetic problem or an electric problem. They're entirely equivalent. All right, so the free energy is this, the elasticity, plus a term that couples the orientation to the magnetic field. So this is the in Jackson you have this magnetic diamagnetic energy.
There's no linear terms are not important.
There are no linear terms in this case. So then you can write this in terms of the orientation of the director relative to the magnetic field. Okay, so then in this geometry, again, Z is vertical, theta is this tilt angle. You can write down the components of the director. You can take these derivatives to get the splay and it says splay and bend. It has no twist. And so then you get an explicit form for this free energy. It has the elastic term, and this coupling to the magnetic field. N dot H is sine theta. All right, this, if you can get an Euler-Lagrange equation from this, but to proceed further, you have to do it's numeric. But if you assume that these two elastic constants are the same, then the problem simplifies to this, where we write the elastic coefficient here divided by the magnetic field in terms of this length, okay? So what's the importance of this length? Well, at low field, that length is large, and nothing happens. As you increase the magnetic field and this length decreases, then the surface orientation becomes decoupled from the bulk at this length. So once the length gets small, then the middle can respond to the field. So now we have this characteristic length. Get the Euler-Lagrange equation. We can do a first integral. Theta m here is the orientation in the middle of the cell. We can do a second integral, and we can get an equation that involves strange special functions, which can then be solved for theta in the middle of the cell as a function of magnetic field.
Well, you said yesterday you would be showing man with bird.
Showing what?
Man with bird.
Oh, yeah, this guy. Actually, Friedrichs died in a Stalin prison camp. Okay, so what do you find? Well, if you look at this initial situation, you see that you put the field on, molecules will end up wanting to tilt, but they don't know whether to rotate clockwise or counterclockwise. So initially, nothing happens. Then, if you take the equation with funny special functions, you see that a good approximation to what happens is this. So nothing happens to a critical field, and then this tilt angle in the middle of the cell goes up as the square root of the field. Now, if you think about making a TV using an electric field, so this is tilt angle, this is electric field, voltage applied to the cell. So nothing happens until you get to some critical voltage. That's not a good situation for making a TV. Make a TV, you want a continuous response.
And D is the thickness?
D is the thickness.
So if it's very thick, then any field will turn. So roughly what
It's very, this depends on thickness. Now in the field case, in the same formula, if you calculated the critical voltage, then the thickness would actually cancel out. So in the electric field case, if you're applying a voltage, then it doesn't depend on thickness.
But here from a microscopic sample, it's almost very, very low field.
Yeah, here, you have to go, the thinner you make the cell,
Okay.
the higher the field you need to get xi. So this critical field is when this, the length becomes sort of comparable to the thickness, or half the thickness.
But it seems like in 3 dimensions, E and H are different because in one geometry, in the E geometry, we still have spontaneous symmetry breaking in the plane, which way they order, which way they tilt. While in the
Right, in
H
the E
direction,
case, they could go back and forth or left and right, yeah, so that's,
seems like that's
that probably will sort of enrich this transition.
So is this result for the 2-dimensional or 3 dimensions?
Well, that's sort of what Leo's just saying, either 2 or 3. I mean, you have a critical field, either 2 or, if we can restrict this to the plane, then that's the problem I solved. If we as Leo said, if you put through the field case, then you have this azimuthal symmetry, so then you have to solve this in 2 dimensions. In other words, when you get close to this transition, then you would have to explore, various possibilities for how this tilt could, happen in 2D.
So the exponential coefficient is independent of the dimensions, meaning the half, 1/2, right?
I think this critical field is independent of dimensions.
Okay.
No, do you have a lot more on this, or?
No, I'm just one. So just the final thought here. So, if you want to make a TV, you don't want this kind of threshold. So in the TVs, what happens is that you pattern the electrodes spatially such that the electric field is not normal to the plates, but it's tilted. So this breaks that degeneracy, and in this case, you get a continuous response from 0 field instead of a transition. Okay.
But you still don't have a complete turn on everywhere if the field is big. It won't.
Yeah, so the electrodes are patterned, right? They're pixelated.
Right.
But the pixels are sort of internally structured so that the fields are oblique. Okay, so tomorrow we'll go to chirality and biology.